Hello, hi everyone. Welcome to the Stone the Brand. This is your Siva sir. Today we are going to discuss about magnetic effects of electric current. Magnetic effects of electric current. So normally the substance which attract the magnetic materials, the substance which has the property of attracting or repelling, okay, that is called a magnet. There are two types of magnets: artificial magnets and natural magnets. So natural magnets are magnetite or lodestone. Magnetite or lodestone is the natural magnet. Artificial magnet, the magnets which are made by the man, okay, those are called artificial magnets. Those are u-shaped magnet, dumbbell shaped magnet, horseshoe magnet, bar magnet. Likewise, there are different magnets are there, different magnets are there. I hope it is very clear. So different types of magnets, those are artificial magnets, man-made magnets, artificial magnets. Okay, so as I mentioned, the substance which has the property of attracting or repelling, okay, that substance is called magnet. That substance is called magnet. So here you can see, if you drop the magnet, into the sand, so at the ends of the magnet, okay, so it will attract the magnetic materials. At the ends of the magnet will attract the magnetic materials. Okay, yes. So those are called poles. Those are called poles. Those are called poles. So the magnet which attract the magnetic materials, okay, so at the ends of the magnet, those are called poles. So those are known: North Pole and South Pole. North Pole and South Pole. North Pole and South Pole. Right? I hope it is very clear. I hope it is very clear. Right? Yes. So here around the magnet, okay, around the magnetic field will be there. Around the magnetic field will be there. Around the magnetic field will be there. The region around the magnet in which magnetic force exert, the region around the magnet in which magnetic force exert is called magnetic field. Or the space around the magnet in which magnetic force exert or it influence act. Okay, so the region around the magnet, the space around the magnet in which magnetic force exert is called magnetic field. Okay, so up to certain region only the magnetic field will be there. Okay, so if you go beyond the point, it won't attract the magnetic material. So up to certain region. So if I take this one, so if I'm considering this a magnet, so within this region only, the magnet will attract the magnetic materials. Okay. So within certain region only, the magnet will attract the magnetic materials. If you move away from the magnet, it won't attract the magnetic materials. Okay, up to certain range only. The region around the magnet in which magnetic force exert is called magnetic field. Okay, so outside of the bar magnet, so if I'm taking the bar magnet, okay, so those are artificial magnet, so that is called man-made magnet, artificial magnet. Okay, so here you can see, so outside of the bar magnet, the magnetic field will be north to south. Outside of the bar magnet, the magnetic field will be north to south. Inside of the bar magnet, the magnetic field will be south to north. Inside of the bar magnet, the magnetic field will be south to north. Okay, so let's discuss about magnetic field and so magnetic field lines, magnetic field and magnetic field lines. Okay, so everything we will discuss about it: magnetic field, magnetic field lines, and properties of magnetic field lines. After that, when the current is passing through the conductor, how it will behave, how the magnetic field will be there around the conductor, in which direction it will be there. So everything we will discuss about it. Everything we will discuss about it. Now we are discussing about so magnet, so magnetic properties, magnetic field lines properties. Okay, so if you suspend the magnet, always it shows north and south direction. If you suspend the magnet, freely if the magnet is suspended, it always shows north and south direction. North and south direction. Okay, so outside of the bar magnet, the magnetic field will be from north to south. Inside of the bar magnet is the magnetic field is south to north. Okay, and coming to the properties. So let's start discuss about magnetic field. Magnetic effects of electric current. Magnetic effects of electric current. Magnetic effects of electric current. So when the current is passing through the conductor, magnetic field will be produced around the current carrying conductor. So when the current is passing through the magnetic field will be produced. So that is what we are saying now. Now you can see here. So magnet is there. Around the magnetic field will be there. So I'm taking the bar magnet. This is a bar magnet. Okay, this is a bar magnet. Okay, this is a bar magnet. So these are the poles. So these are the poles of the bar magnet. So at the ends only it will be there. Exactly at ends. So little inside will be there at the ends. So certain region only. So around the magnet, the magnetic field will be there. Around the magnet, the magnetic field will be there. The magnetic field will be up to certain range only. So beyond the point it won't. Attract the magnetic materials. Up to a certain region only, the magnet will attract the magnetic materials. That is called magnetic field. Okay. So up to a certain region, the magnet will attract the magnetic materials. That is called magnetic field. Okay. So the magnetic field will be in the form of field lines. Magnetic field will be in the form of field lines. Magnetic field will be in the form of field lines. Okay. So how the field lines will be around the magnet? Around the magnet, the magnetic field lines from north to south. Around the magnet, so the magnetic field lines are north to south. Inside of the bar magnet, the magnetic field lines are south to north. We'll see here. So around the bar magnet, the magnetic field will be north to south. So this is the magnet. So you can check here. Okay, so this is the magnetic field lines. Okay, so this is about magnetic field lines. So around the magnetic field will be there. So from north, those field lines are emerging out, and to the south, those field lines are merging. Okay, outside of the bar magnet, the magnetic field will be north to south. Inside of the bar magnet, the magnetic field will be south to north. Right? So we'll discuss few points. First one is so magnetic field. Second one is magnetic field lines. Magnetic field lines. field lines. Coming to the third one, so we'll discuss about properties of magnetic field lines. Okay, so after that, that's enough only. So about these 2 points, anyway, properties will comes under magnetic field lines only. So point number 1 already discussed. So the region or the space around the magnet, the region or space around the magnet in which magnetic force exert. The region around the magnet or the space around the magnet in which magnetic force exert is called magnetic field. Coming to the properties of the magnetic field. Properties of the magnetic field. So point number 1. So magnetic field lines emerge out from north, measured south. Outside of the bar magnet, magnetic field will be from north to south. Inside of the bar magnet, from south to north. And coming to the next one. So these field lines never intersect. Magnetic field lines never intersect. So normally if you want to identify the magnetic field direction, at a particular point in the magnetic field. Okay, so we know that magnetic field direction outside north to south. We know that. But at a particular point, if you want to identify the magnetic field direction, you have to draw the tangent to the magnetic field line. So you have to draw the tangent. Okay, so I want to know the magnetic field line direction at this point. So I want to know the magnetic field line. So magnetic field direction at the particular point. So I want to know. So what I have to do? I have to draw the tangent. To the magnetic field line. Now if I draw the tangent to the magnetic field line, then along that direction the magnetic field will be there at that particular point. The magnetic field direction will be represented by drawing the tangent to the magnetic field line. Okay, if you draw the tangent, automatically along the direction magnetic field will be there. In that particular point. So overall we know that. Okay, so here around the magnet, how the magnetic field will be north to south, inside south to north. We know that. But I want to know that magnetic field direction at the particular point. So here I want to know. So we know that overall, but we want to know at a particular point means you have to draw the tangent to the magnetic field line. Okay. So magnetic field will be in the form of field lines. Magnetic field. We know that magnetic field. What is that magnetic field? The space of the region around the magnet in which magnetic force exert. The region or the space around the magnet in which magnetic force exert is called magnetic field. We know that magnetic field direction outside of the bar magnet, north to south, that is a free north pole direction. Okay, if you place the compass, okay, so if you place, understood? So if you place the compass here, near to the magnetic field, because of the magnetic field, the compass gets deflection. Means deflection will be shown in the compass. Automatically. So needle in the compass will move. So actually, what is the needle present in the compass? So that is also a magnetic field, magnetic needle. So it has the properties of the magnet. Okay, so if you place one more, this is magnet. Okay, so I'm taking this is north, this is south. It will attract. And this is north, this is also north. then it will repel. And south south repel, north north repel, north and south attract, south and north attract. Two dissimilar poles will attract. Two dissimilar poles will attract. Okay, two similar poles will repel. North south attract, south north attract. Okay, so south south repel, north north repel. Okay, so two similar poles will repel each other. Two dissimilar poles will attract each other. Understood? So that is about the magnetic field and properties of the magnetic field and the direction of the magnetic field at the particular point. How to find out the direction of the magnetic field at a particular point? So we have to draw a tangent to the magnetic field line. You have to draw a tangent to the magnetic field line. If you draw a tangent to the magnetic field line along that particular direction, so we can identify the magnetic field direction at particular point. Okay, so you have to draw the tangent. Understood? So I hope it is very clear. Right? So now we will discuss about one more. Magnetic field is over. Magnetic field lines, properties of magnetic field lines also completed. So now we will discuss about electromagnet. So you can observe in the lower classes we do that. So taking an iron nail, wrap a copper wire. Okay, so copper wire to the iron nail and connect to the battery. So take a iron nail. Okay, iron nail. So wrap copper wire. So wrap a copper wire around it and connect to the battery. Then what happens? Current will flow through the copper wire. Then iron nail act as a magnet. Automatically this iron nail will attract the magnetic materials. This iron nail, so because current is passing through the iron nail, it acts as a magnet. So that magnet will attract the magnetic materials. Will attract the magnetic materials. Okay, magnetic materials. Understood? So that is only electromagnet. I hope it is very clear, right? So now we are going to discuss about current carrying conductor act as a magnet. So I am taking thick copper wire, connect to the circuit. Okay, so be careful. So and observe carefully. So I'm connecting straight copper conductor to the circuit. Then current will passes through it. It acts as a magnet. Then we will discuss all those points. Okay, let's start. We will discuss all those points, what exactly happens. Okay. So I am taking this the conductor, straight copper conductor like this. So this is the straight copper conductor. So that is connected to the ammeter. Here is ammeter and resistor. So rheostat. This is rheostat. Okay. So you can see here. So now battery. This is the battery. This is a battery. I am connecting to the battery. Okay, switch is here. Current is passing through it like this. Okay, so here is ammeter. This is a rheostat and ammeter. So thick copper wire. Okay, so I hope it is very clear. Thick copper wire, thick straight copper conductor, connected to the circuit. Okay, connected to the circuit. Now, current is passing through the straight copper conductor. Okay, so we know that if the current is passing through the conductor, it acts as a magnet. So magnetic behavior will be shown in the conductor. So it will attract the magnetic materials. That is nothing but, so it exhibit the magnetic properties. Yes or no? If you place compass near to the conductor, automatically deflection will be shown. Right? Yes. So deflection will be shown in the compass. So Hans Christian Ørsted observed that, so when a compass is placed near a current carrying conductor, got deflection. Okay, so compass is placed near to a current carrying conductor, then it's automatically gets deflected. Why? So in the compass, magnetic needle is there. Okay, so when the current is passing through the conductor, it acts as a magnet. It also acts as a magnet. So as we know that magnetic properties, north repel, south repel, north south attract, south north attract, right? I hope it is very clear. So the same thing here also, if the current is passing through the straight copper conductor, so it acts as a magnet. So you can see here. So I'm taking like this. Okay, so here if you place the compass near to a straight thick copper wire, then automatically deflection will be shown. Okay, deflection will be shown, right? So here it will be shown. And one more thing, around the conductor, magnetic field will be created. Yes or no? Magnetic field will be there. Magnetic field will be in the form of concentric circle. Magnetic field will be in the form of concentric circles, like a closed loops around the conductor. So if more crowded magnetic field represent around the conductor, then more magnetic field lines are crowded at the point. Okay, more magnetic field lines are crowded at particular point means more magnetic field will be there. Okay, so around the conductor, the magnetic field will be in the form of concentric circles. So if you move away from the conductor, the magnetic field will be decreasing. Near to the conductor, magnetic field will be more. If you move away from the conductor, magnetic field will be less. Magnetic field will be less. Okay. So here you can see. So I am taking this the conductor, straight copper conductor. So I am taking around this one. Magnetic field will be here. Around like this. The magnetic field will be like this. Okay. So magnetic field will be created. Current is passing. So those are closed loops, concentric circles. We know that one. Okay. So if the current is passing from, so we know this the north and south. This is north, south, east and west. North, south, east and west. So current is passing from north to south. Current is passing from north to south. How the deflection in the compass? Okay. So how it will be? How the magnetic needle moves? So if the current is passing downward direction, that is nothing but north to south, deflection in the compass will be towards east. Deflection in the compass will be towards east. If the current is passing from, if the current is passing from south to north, the deflection will be in the compass towards west. Towards west. Understood? So current is passing from north to south, deflection will be towards east. Current is passing from south to north, deflection will be towards west. Towards west. Understood? Towards west. So, sir, how can you say like that? So you are saying current is passing from north to south, deflection will be towards east. If the current is passing from south to north, deflection will be towards west. How can you say like that? By what base? By which rule you will follow? And how can we identify that deflection? Okay. How can we identify the magnetic field direction around the current carrying conductor? How can we identify the magnetic field direction around a current carrying conductor? By using right hand thumb rule. By using right hand thumb rule, we can identify the magnetic field direction around the current carrying conductor. Suppose if the current is passing along this direction, so right hand thumb. So this is my right hand. This is the thumb. So thumb shows along the current direction. Curly fingers, folding fingers, rotating fingers. Okay. So this curly finger shows the magnetic field direction. Okay. Curly fingers, folding finger shows the magnetic field direction. Magnetic field direction. So if the current is passing this direction, then so magnetic field will be like this. Okay. If the current is passing like this, so magnetic field will be like this. Understood? If the current is passing upward direction, magnetic field will be like this. If the current is passing downward direction, the magnetic field will be like this. Okay. So according to the current direction, we can identify the magnetic field direction. Okay. So according to the current direction, magnetic field direction can be identified. Okay. So if the current is passing like this, so folding fingers, curly finger shows the magnetic field direction. Magnetic field direction. Understood? So like that. So here you can see if the current is passing downward direction, current is passing from north to south, current direction. Okay. So I can say I is moving from north to south. Yes or no? I is moving from north to south. The magnetic field will be so like this. Understood? So according, like you can say, and here also like this. Understood? If you change the battery direction, okay. So if you change the battery direction, current, if you change the battery direction, that is nothing but current direction. So battery is, so positive terminal, negative terminal. If you change the direction of the current, magnetic field direction also changes. Very important. If you change the current direction, If you change the current direction, magnetic field direction also changes. Okay. So how can we identify the magnetic field direction around a current carrying conductor? By using right hand thumb rule. By using right hand thumb rule. So if the current is passing upward direction, curly fingers, folding finger showing the magnetic field direction. So along the current direction, place the thumb finger of your right hand and fold if the fingers, fold the remaining fingers. So along the folding fingers direction, the magnetic field will be there. That is called a right hand thumb rule. Right hand thumb rule. I hope it is very clear. Understood? Yes. So if the current is passing from north to south, the magnetic field will be there. If the current is passing from south to north, so the magnetic field direction also changes. Magnetic field direction also changes. I hope it is very clear. So this is about so current passing through the straight copper conductor, right? Yes. So now we will discuss about one more. So this is about straight conductor. If I take loop, so here I mentioned so 2 point. Point number 1, near to the conductor magnetic field will be there. More crowded magnetic field lines represent more magnetic field. If you move away from the conductor, magnetic field decreases. So if you increase the current, magnetic field also increases. So magnetic field is directly proportional to current passing through the conductor. And the next point is, if you change the direction of the current, magnetic field direction also changes. If you change the direction of the current, magnetic field direction also changes. Magnetic field direction also changes. Understood? I hope it is very clear. This is about straight copper conductor. Okay. Now I am taking loop. Okay, so next one is loop. Loop I am taking. Here you can observe. This is the loop. So this is the loop. This is the loop I am taking like this. So current is passing like this. Current is passing. Around it will be magnetic field will be there. Around this one magnetic field will be there. Understood? So like this it will be there. And here also magnetic field will be there like this, like this, like this, like this, like this, and like this. Okay. So here you can see, and here you can see, here you can observe, here you can observe. So at the center it will be straight lines. At the center it will be straight lines. So where the magnetic field will be more? So in which place the magnetic field will be more? So at the center, add a circumstance. So where it will be? Magnetic field will be more at the center than at the circumstance. Okay. So how, sir? How you are saying magnetic field will be more at the center compared to the circumstance? Because as I mentioned, so current is passing like this. Okay. So by using right hand thumb rule, so current is passing. So magnetic field is moving away like this. Okay, like this. And here, so it is leaving like this, north. And here, moving, reaching. And to this point, reaching. So this is south. Understood? I hope it is very clear. So from the point, if the magnetic field is leaving, from the particular point, if the magnetic field is leaving, that point is called North Pole. That point is called North Pole. If the magnetic field is reaching to the particular point, if the magnetic field is reaching to the particular point, that point is called South Pole. That point is called South Pole. Understood? I hope it is very clear. Now, so magnetic field is leaving the point, that is North Pole. Magnetic field is reaching the point, that is South Pole. I hope it is very clear. clear. Understood? Understood? Right? Next one. So now you can see. So if the magnetic field lines are reaching to the center, it will become straight lines. One magnetic field, okay. So one magnetic field will add up to the another magnetic field. One magnetic field will be add up to the another magnetic field. So it is adding one to each other. Then what happens? Then so more magnetic field, uniform magnetic field will be created at the center than at the circumstance. At the center. Understood? So uniform magnetic field, more magnetic field will be at the center. Yes, yes. So this is about the loop. Now, so we'll discuss about a solenoid. Solenoid, solenoid. Solenoid, solenoid, solenoid. Solenoid, solenoid, solenoid. So here I am taking the solenoid, means take a straight copper wire. Take a straight copper wire. Okay, so insulated copper wire. Wrap in the form of cylindrical shape. Wrap in the form of cylindrical shape. Connect to the battery. Connect to the battery. It act as a magnet. It act as a magnet. So like this I am taking. Near to the conductor, near to the conductor, near to the conductor. So battery switch. Battery switch, current is passing. Positive terminal, negative terminal. Okay. So if the current is passing through the solenoid, it acts as a magnet. We know that. If the current is passing through the solenoid, it acts as a magnet. So you can see here. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. So you have to take 3 lines up, 3 lines below and leave in the middle 3 lines. Okay. So join these 3 lines. 1, 2, 3. Next 3 more lines. 1, 2 and 3. So 3 lines, 3 lines, 3 lines. 3 lines, 3 lines, 3 lines. We know that if the magnetic field is reaching to the point, that is south. If the magnetic field is leaving the point, leaving that point, so that is north pole. This is south, this one is north. This is leaving, sorry, leaving, so this is north and reaching to the point, this is south. Leaving the pole, north, leaving the point, so reaching to the point, reaching, and leaving, and here towards north, and here so understood? So around the magnet, so you can see here, so the magnetic field will be from north to south and leaving, so here it is leaving, here it is reaching, so from this point it is coming. Understood? I hope it is very clear. So yes, So based on that clock phase rule, and also how you wrap the conductor. So if I'm taking this the conductor, if you wrap above it, if you look at it, so current is passing clockwise direction. So this is a clockwise direction. So if you wrap the conductor below it, so if you are taking below it, so current is moving anti-clockwise direction. Understood? So by using right hand thumb rule also we can identify the direction. So but from according to the textbook, we can conclude that. So so from this side we can take north, and from this side we can take south. So by using right hand thumb rule, we can identify. So if the current is passing, the magnetic field is like this. Yes or no? So the magnetic field, current is passing downward direction, right? So this is the current direction. If you place, the magnetic field will be like. So this is the magnetic field direction. Understood or not? So by that we can identify the poles, north pole and south pole. And one more thing. So clock phase rule. By using clock phase rule. So this is a clock phase rule. So if the current is moving in anti-clockwise direction, that is north. If the current is moving clockwise direction, that is south. Okay, south pole. Understood or not? That is a clock phase rule. I hope it is very clear. Right? Yes. Okay, so I hope it is very clear. So next one. So this is solenoid. Take a straight copper wire, insulated copper wire. So wrap in the form of cylindrical shape, connect to the circuit. So current is passing through the conductor. It acts as a magnet. So here one point is, so solenoid and bar magnet. Okay, solenoid behaves as a bar magnet. It acts as a bar magnet. Understood? So I will tell few differences and similarities between bar magnet and solenoid. So I will discuss those points. You can see here. So this is a bar magnet. So I am taking this a bar magnet. Understood? This is north and this one is south. And here you can observe the magnetic field will be from north to south. Understood? I hope it is very clear. So magnetic field will be from north to south. So here also solenoid also magnetic field will be north to south. Inside of the bar magnet, south to north. And one more point, here you need to understand one thing is, so here you can see, here you can observe one thing. So in the solenoid, we can able to improve the magnetic field. Okay. So how can we improve the magnetic field? Here in the bar magnet, we can't improve the magnetic field. But so in the solenoid, we can able to improve the magnetic field. How can you improve the magnetic field in the solenoid? By passing more current. So it depends on strength of current, point number 1. And point number 2, increasing the number of turns. Okay, if you increase the number of turns, magnetic field increases. If you send more current also, magnetic field increases. So in a bar magnet, we can't able to do anything. We can't able to improve the magnetic field. Magnetic field is fixed. But here we can able to change. And one more thing, this is a permanent magnet. This is temporary magnet. So permanent magnet and temporary magnet. So whenever we want this, so as a magnet, if you send the current, it will act as a magnet. So here, no. So it is fixed. So magnetic field is fixed. So magnetic power also fixed. Okay. So we can't able to increase the magnetic field. So we can't able to decrease the magnetic field. Here we can able to do it. Okay. So if you want to increase, we can send more current. If you want to decrease, we can send a less current. And we can improve the number of turns. If you increase the number of turns also, more magnetic field will be produced. Okay. And one more thing, if you suspend the solenoid freely, automatically it acts as a magnet. It shows the north and south direction. How you are suspending the bar magnet always shows north and south direction. Same like that. So solenoid also will shows north and south direction. Solenoid also will shows north and south direction. Solenoid also will shows north and south direction. Understood or not? And one more thing, we can change the polarities. Those are north pole, south poles are there, right? North pole and south pole. So those poles can be changed. We can able to change. How can you change in the solenoid? So by changing the battery direction, by changing the current direction. So if you change the battery polarities like a north pole, south pole, automatically poles of the solenoid also can change. Poles of the solenoid also can change. Yes. So but here we can't do anything. So here it is fixed. So those are the similarities and dissimilarities of solenoid and bar magnet. I hope it is very clear. Now, so we'll discuss about next one. So here if you are taking the same, so we can able to magnetize the soft iron by placing inside of this solenoid. So that is electromagnet. So that's enough. Now we will discuss about current carrying conductor placed in the external magnetic field experience the force. Current carrying conductor placed in the magnetic field experience the force. So I am taking here so this is stand I am taking here. So here supporting rod. Okay, so I am taking this aluminum rod AB. Okay, so it is placed in the so north pole and south pole. Say current carrying conductor placed in the external magnetic field experience the force. A current carrying conductor placed in the external magnetic field experience the force. Understood? So I am taking like this. This is the battery. Na na ni na 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 ni na ni na ni na na ni na ni na 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 ni na ni na ni na ni na ni na ni na 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 A current carrying conductor placed in the external magnetic field experience the force. In which direction the force will act on the conductor? In which direction the conductor will move? That is the question. Okay. By using Fleming's left hand rule. So magnetic field, index finger represent magnetic field, middle finger shows the current and thumb finger shows the force acting on the conductor. Okay, so index finger, middle finger and fourth thumb finger. So index finger represent the magnetic field. So middle finger represent the current thumb finger represents the force acting on the conductor. So if you place like this, so this is a north pole, south pole, and you can take the current direction. So in which direction the thumb is showing? Inward. So thumb is showing inward. So Fleming's left hand rule. This is the Fleming's left hand rule. Okay, so place the index finger along the magnetic field direction. Place the index finger along the current direction, and place, so lift your thumb. Along the thumb direction, the force will act on the conductor. So conductor will move towards the board. So thumb is showing into the board. Conductor will move into the board. Understood? I hope it is very clear. So like this. So this is about the Fleming's left hand rule. Clear? Understood? So that's enough. So next one, short circuit. Short circuit is nothing but the direct contact of live wire and neutral wire takes place. Sometimes insulation of the wire may turn. Okay, so that time what happens? The direct contact of live wire and neutral wire takes place. Then heavy amount of current will be drawn from the mains. Point number one. And coming to the point number two. So overloading, high voltage appliances. Okay, high voltage appliances are too many appliances connect to the circuit at a time. High voltage appliances like so geyser, washing machine, AC, fridge. So these type of high voltage appliances on at a time. Okay, then heavy amount of current will be drawn from the mains. Then it may lead to the short circuit. Understood? So that is about overloading. So I hope it is very clear. It's about magnetic effects of electric current. If you like the content, if you like the channel, if you like my explanation, please do like, share, and subscribe to Student Brand. So those who are in 10th class, please share to everyone. Ask your friends to join to the class. So spread one word regarding the channel. So do support the channel. Do encourage the channel. So please kindly encourage the channel and support the channel. Share to everyone. Ask your friends. So ask those who are there in the 10th class CBSE grade 10 physics, and so those are writing for JEE and NEET students, and those are studying grade 11, grade 12, and whomever. Okay, so right from 6th to 12th they can attend the classes. These are all important points only. It will be helpful for them. Okay, so I hope it is very clear. So thank you so much. We'll see you in the next class. Signing off.